Welcome to our presentation on participatory dam decision support. I am representing the team of researchers you see here and the work we conducted together in 2018 to 2020 as part of the multi-state, multidisciplinary Future of Dams project. Including and in addition to my co-authors, I just wanted to acknowledge the support and involvement of many other people in this and related work in the Future of Dams project. Sam Roy, who was an assistant professor in the Mitchell Center at Maine, but now has moved on to another job. Bridie McCreevy, who is an associate professor of communication and journalism at Maine, and her former PhD student, Tyler Quiring. Natasha Luchenka, PhD candidate from the University of New Hampshire, mentored by Dr. Kat Ashcraft, and Billy Winslow, software engineer at UNH, who was instrumental in getting our model up and running. Also, our Future of Dams colleagues across 3 New England states representing disciplines as diverse as geomorphology and environmental communication. The United States has many dams across the United States that are generating hydropower, across the country, that are generating hydropower. You can see most of them are clustered in the west, southeast, and northeast. The northeast is unique because most dams are less than 100 megawatts in power capacity, which means there are a lot of them spread out over rivers to add up to the capacity they provide. While they provide cheap renewable electricity to the region, they also block rivers, which causes negative environmental and cultural impacts. Nearly 300 of these hydropowered dams are coming up for relicensing across the country in the next decade, around 45% of which are in the Northeast. Relicensing is a key opportunity that only comes around every 30 to 50 years to reassess or reevaluate the dam infrastructure in the public waterway and think about the environmental, economic, and social impacts of the dam. Although FERC, the dam owner, and a collection of state and federal agencies are the official decision makers, other members of the public can plug into the process through public comments, public hearings, or as a legal intervener in the process. Dam decisions are complex and often involve a need to balance conflicting management objectives. Multi-criteria decision analysis, or MCDA, is a unique framework that helps people balance competing objectives, making trade-offs explicit and providing recommendations based on data and preferences. MCDA extends the idea of cost-benefit analysis to include qualitative data more easily and does not require monetization, which can be a complicated and uncertain process for ecosystem services. MCDA is an umbrella term for a suite of mathematical models and stakeholder engagement processes that quantitatively consider multiple decision criteria and alternatives without requiring monetization. There are 5 main steps, including identifying decision alternatives and criteria, collecting data to create a decision matrix, selecting a normalization procedure to make decision criteria data with different units of measurement comparable, eliciting preferences from stakeholders about each decision criterion and alternative, and creating a mathematical model to combine data from the decision matrix with user-defined preferences into a ranking or score. These 5 steps necessitate that MCDA be both a model and a process. The model is a quantitative representation of a complex decision that includes multiple decision criteria and alternatives, culminating in a transparent way to rank choices based on data and preferences without needing to apply monetary values to criteria that are difficult to monetize. There are many different computational methods that fall under the umbrella term MCDA and limited practical use in energy or watershed decision-making, or in single versus multi-dam comparisons. The process speaks to the participatory side of MCDA, how people engage in it. MCDA can be used as a researcher-created model, and the end result calculations can live in academic papers and presentations. Most MCDA models proceed this way, but participatory MCDA implies that people interact in some way with the model by doing some or all of identifying decision criteria and or alternatives, identifying relative preferences for decision criteria, actually using the model, individually and/or as a group, engaging in discussion that identifies shared or negotiated group preferences, comparing individual and group results, and participating in iterative design of the model and/or process, all of which can happen in a single and/or multiple dam focus. I've made some of these ideas appear in blue and bold here because they represent research gaps our work seeks to fill. More specifically, we have been interested in which decision criteria and alternatives do stakeholders in hydropower dam decisions consider important? Can MCDA help stakeholders with diverse viewpoints consider multiple alternatives and criteria in a transparent way and gain a more complete understanding of the wide variety of issues? And can MCDA help groups of stakeholders with diverse viewpoints achieve agreement on dam decisions? To address the research questions, we used an iterative stakeholder-engaged approach to MCDA model and process design and testing that developed, grew, and changed a lot over the 4-year grant timeline. We started with a literature review of what has been published about participatory MCDA for watershed and energy decision-making to try to determine which specific MCDA model and process approaches to use in our work. In addition, we conducted 14 stakeholder interviews and coded 14 additional interviews that were conducted by Bridey and Katz research teams. These activities helped us create a decision matrix with decision criteria and alternatives identified by literature review and stakeholder interviews. From there, we were able to develop iterative versions of a quantitative MCDA model that we tested in a series of 3 workshops. Our literature review, which we will be submitting for publication, provides an overview of the variety of existing MCDA methods, both modeling and process, and a review of 24 group participatory MCDA and some non-MCDA studies of water resource and energy applications organized by MCDA type. We present a 2-dimensional assessment or rating of each article's depth of stakeholder participation and model complexity to help inform which approaches may be better suited to which applications. The stakeholder interviews were developed over a 1 to 2 year process with Future of Dams collaborators across 3 states that were part of the Stakeholder Engagement Working Group. We met regularly via Zoom, even before COVID-19, and co-developed an interview protocol and institutional review board application, identified a list of potential interviewees, categorized interviews by stakeholder type, conducted some interviews together, and shared interview field notes and transcripts. Emma coded 28 of these interviews, spanning 8 stakeholder categories, including 14 that she led herself. The literature review and interviews informed our decision matrix for the MCDA model, which includes 5 decision alternatives and 14 decision criteria. We didn't have sufficient data on 6 of the decision criteria, so we used our workshop pre-survey to collect data based on the knowledge and perceptions of the workshop participants. But future analysis that builds on this work should conduct targeted social science studies to systematically collect data on these criteria. Traditionally, MCDA is applied to one problem or site at a time, but Sam Roy had developed an incredible multi-objective genetic algorithm for the entire Penobscot watershed, which was appealing for applying MCDA to a multi-dam context. However, after applying the watershed scale to our first 2 workshops, we realized it was too big to be meaningful to participants in a 1-day workshop. So we ultimately scaled it back to the 8 dams coming up for relicensing on the Penobscot River in the next decade. This includes West Enfield, Ripagenas, Medway, and 5 dams that are part of the same FERC license, collectively called Penobscot Mills, and represented here in blue font. Here is a look at the 8 dams included in our study, with 5 run-of-river projects and 3 store and release, or conventional dams with reservoirs. Power capacities range from 3.4 to 37.5 megawatts, with one dam, Millinocket Lake, not powered at all. It has no hydropower equipment, but it is licensed under a project that lumps it with 4 other dams. Altogether, electricity generation from the 7 existing dams adds up to around 6% of Maine's annual electricity generation. Increasing power capacity at dams for which that is feasible would increase that share to 8%. We collected data on each dam for each decision criterion and alternative and completed a decision matrix. The partial table you see here, with decision criteria listed in the first column, the decision alternatives up top in the first row, and the data for each decision criterion and alternative within the cells. To use the decision matrix in the MCDA model, we needed to normalize the data because each decision criterion is measured in different units. So they cannot be used in an equation together, along with the preference weights we were eliciting from the participants. These are the equations that we used to normalize the data. And this matrix shows how normalization converted the original data that were measured in these units into scores between 0 and 1. Originally, we selected Analytical Hierarchy Process, or AHP, as our preference elicitation method, and created an Excel-based tool with Visual Basic coding that looked like this. We selected this approach because AHP allows users to make pairwise comparisons between different decision criteria and alternatives, thereby allowing them to only think about one thing at a time. However, in practice, this caused users to go through over 100 iterations of pairwise comparisons and was, in practice, too unwieldy, as we discovered at our first 2 workshops. We were also working with a full watershed scale at this point, which was too overwhelming for participants to think about. Our final version of the model was created in R through the Shiny application and used weighted sum MCDA, a much simpler approach that was easier for users to understand and interact with. In this version, users can see a map of the 8 dams and some technical information on each. Then they click on each dam and move a slider bar to enter preferences for each decision criterion for each dam, with a requirement that the total preference score must sum to 100. Users are encouraged to look at dam fact sheets we created that provide a summary of the dam and the dam-specific decision matrices, while making their selections to consider the relative quantitative importance of each decision criterion at each dam. Behind the scenes, the model does a simple calculation that multiplies each data point in the normalized decision matrix by the preference weight elicited by the user for each decision criterion, and then adds up each column for a total score across all decision criteria for each decision alternative for each dam. The main model results look like this, with a cluster of 5 bars for each dam, with each bar color representing a different decision alternative. The tallest bar in each cluster represents the preferred decision alternative for each dam based on the user's own preferences and the scientific data from the decision matrix. The example shown here uses hypothetical preferences for all 14 decision criteria, with preferred decision alternative model results ranging from remove dam to improve fish passage, to improve fish passage and hydropower capacity, depending on the dam. Users can also see how much each decision criterion contributed to the final score. This graph is for the same hypothetical example from the previous slide. There are many other graphs and tables the user can see to view results in different ways and to dig deeper into the underlying data in the model at each step of the MCDA. Developing the final version of the model was a hefty undertaking with many iterations, including the 2 main ones I just went over. The AHP and weighted sum versions, but each of those had several sub-iterations as well. Designing the workshops was also a hefty undertaking. These were the goals we had for each workshop. In this context, although it was important for the MCDA tool and components to be accurate, It was more important that it was user-friendly and could help facilitate a group negotiation about dam decision-making. In all, we had 3 workshops that contributed to our overall case study results. Study 1 used the AHP model with researchers from the Future of Dams team as the participants. Study 2 used an earlier version of the weighted sum model that had a watershed scale focus and incorporated Sam Roy's multi-objective optimization algorithm. Study 3 used the version of the weighted sum model I just showed. Each workshop included a pre- and post-survey, researcher observations and reflection, and the MCDA results that came out of various model versions. This table summarizes the 3 studies by workshop date, time allotted, number of dams included in the workshop, number of participants, participant type, software, MCDA, and whether Sam Roy's multi-objective optimization was used or not. I am going to give a little more information about the workshop that was part of Study 3 because this was the main focus of the work in many ways. We learned through the 2 prior workshops that the stakeholder workshop in October 2019 was going to need a lot more visuals to help participants understand what the MCDA model was trying to do. So I created a poster like this for each dam with information from the fact sheets up top and the decision matrix below, and 2 posters describing in detail the calculations and data sources for each of the 14 decision criteria. Here is the second of these 2. I also created a poster for the decision alternatives and for explaining the MCDA method. The 2 previous workshops had been 2 to 4 hours each, with participants doing a fair amount of prep work on their own, namely the individual preference elicitation. Based on those experiences, we decided users needed to do the individual preference elicitation in person with us so we could walk them through it and answer questions and observe. So the final October 3rd workshop became a full-day affair here at Maine in the Mitchell Center, where we spent the morning getting to know each other, learning about MCDA through a presentation we prepared just for the workshop, and conducting the individual preference elicitation activity. We had social time and food worked in to provide space for participants to get to know each other informally, as well as the more structured workshop activities. In all, we had 9 participants in our October workshop who represented these entities that all have a role in the decision process along the Penobscot River. Unfortunately, despite repeated attempts, we were unable to get a hydropower developer or owner to attend. In the beginning of the workshop, we discussed a set of 5 group commitments guided by an intention for the day. We also offered the opportunity for participants to add other commitments. We supplied each participant with a computer and had them work through the 14 decision criteria and 8 dams in the Shiny app individually in the morning. Then, after lunch, we did a group negotiation process where we put up the averaged preferences from the group for one of the dams. We designed the app to automatically average the group preferences and stepped through each decision criterion to see if the group could come to agreement on where each slider bar should be. The process took about an hour for one dam, and so we only got through one dam by the end of the workshop. It seemed at first that we were not going to reach agreement, but at the last minute, one of the participants proposed taking the preference points from all of the low-performing criteria and distributing them to the criteria the group had been negotiating over for the last hour as the most important. Ultimately, the group reached an agreement and a set of slider bars that everyone could live with. This graph shows the change from where the slider bars started in the beginning of the group negotiation process, at the non-weighted average of all participants' individual preferences for the morning individual activity, shown in gray, to the final agreement for the West Enfield Dam, shown in blue. You can see, based on the one participant's recommendation, the group moved the low preference points for public health, aesthetics, historical importance, number of properties impacted, and breach hazard potential mainly to indigenous cultural traditions and lifeways, recreation, and sea-run fish habitat area. With half of the group's preference weight applied to sea-run fish habitat area and another 20% to indigenous cultural traditions and lifeways, it is no surprise that the group's highest MCDA score for West Enfield was for the decision alternative, remove dam. Across the 3 studies, we were able to identify several aspects of participant reactions to help inform how useful our model and process was to the user. In general, we saw improvement with each study. For example, in the first 2 studies, participants saw the model as a black box, but by study 3, they did not. They also found the decision criteria understandable, but still with some needed improvements to make them more understandable. They found the preference elicitation clear and user-friendly, the MCDA understandable, and did not leave feeling like more data were needed. They also found the graphed MCDA results believable, so they had trust in the model, at least to a certain extent. Overall, we found that the final version of the model provided site-specific information, some of which was synthesized from FERC licenses, which improved access to information for participants. The model also provided an interactive space for learning about how preferences impact MCDA recommendation, thereby enhancing capacity for participants to become involved in dam decision processes. Many participants noted that the model could have a role in opening up conversation before it becomes contentious and divided, thereby also enhancing capacity. And finally, even though every dam is different and every FERC licensing is different, the Dam Decision Support Tool, or DDST, seems to have a potential role to play in planning for relicensing. You can learn more, access, and download all of the final workshop materials, including the poster templates, fact sheets, decision matrices, workshop agenda, and play around with the model at this website. You will need to create a login to use the model, but it is free. The model is also open source, so you can download the code and, if you know R, adapt it to your purposes. Thank you to the following groups that supported this work. Please feel free to email me if you have any questions.